Welcome to the video lecture on derivatives of inverse functions. We're going to start by talking about a couple of theorems that will enable us to figure out what the derivative of the inverse of a function is, especially if we can't find the formula for what that inverse function happens to be. So the first theorem says that let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse is also continuous on its domain. If f is differentiable at c and the derivative at c is not 0, then f inverse is differentiable at f of c. Now this next theorem is the one that's more useful to us. It's going to give us a way of figuring out the derivative of an inverse function. So suppose that we have a function f that is differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which the derivative of f at g is not 0. And here's the formula that we're going to be using. The derivative of this inverse function g is defined to be 1 over the derivative of f evaluated at g, assuming that that denominator does not become 0. So the derivative of your inverse is 1 over the derivative of your original function evaluated at g. So let's see a typical example of how you would use this formula. Suppose that we have our original function f is x to the fifth minus x cubed plus 2x. We're going to let g be the inverse function of f. Now if you wanted to find out what that inverse formula would be, the way we would normally do that is we would take our function f and we would let it equal to y, and then we would swap our x's and our y's, and then we would try and solve this for y and figure out what it was in terms of x. Now that's the hard part, because trying to solve this equation right here for y is nearly impossible to do. So trying to do that so that we could then take the derivative of this resulting equation is going to be impossible, since we can't come up with what this formula should be. So here's a way to get around that. We're going to use the formula for f to help us get the derivative for g. So here's what we do first. First, if we want to know the derivative of g at 2, which is our eventual goal down here in part B, what we're going to do first is find the value of g when x is 2. Now think about this. F and g are inverses of each other. So if we want to know what happens to g when x is 2, where does g send to? I don't know. But I do know that because g and f are inverses, whatever g sends 2 to, whatever this question mark is, that function f has to swap the x's and y's, so it sends that question mark back to 2. And that's that inverse relationship between f and g. So since I don't know a formula for g so that I could just plug in 2, remember we couldn't solve this up here. What we're going to do instead is we're going to figure out where f goes, or what value of x sends f to 2. We're going to figure out what this question mark should be, what this x should be, so that we end up with an output of 2. So what I have to do is I take my function f, which is equal to x to the fifth minus x cubed plus 2x, and I'm going to find out where that equals to 2. When does that have a y value of 2? Well, that's not so easy to solve because it's a fifth degree equation. So what I would want to do is either just try some trial and error, or you could pull up your calculator. And what I've done is I've typed in my function into y1, so I have x to the fifth minus x cubed plus 2x, and I want to know when it hits 2. So in y sub 2, I'm typing in just the function 2, a horizontal line at a height of 2. If we hit graph, we're basically looking to see where these two graphs are going to intersect, so I can figure out what that x value is. So if I do a simple intersect command by going to calc, number 5, and I'm just going to arrow up to where these two curves intersect and hit enter 3 times. It tells me that when x is 1, the y value is 2. And you can see just by plugging in, if x was 1, we'd get 1 minus 1, which is 0, plus 2, and that does equal to 2. So this equation is going to be true when x is 1. So the solution to this is x equals to 1. So now we know the value of this when x is 1. So we're going to use that now to find the derivative of g. Now we didn't have a formula for g, so how are we going to find its derivative? Well, that's what this formula up here is all about. According to this formula, g prime at 2 is going to be 1 over f prime at g of 2. And that's going to be 1 over f prime of what? What is g of 2? Remember, we said that we figured out that when this x right here was 1, f sent 1 to 2, therefore g sends 2 to 1. So that means g of 2 is equal to 1. So we need to plug in 1 into our derivative of f, take the reciprocal of that, and that will tell us the value of the derivative of g at 2. So these two numbers here kind of go together. When x is 2, y was 1, or when x was 1, y was 2. There's that inverse relationship between those two ordered pairs, that swapping of that x and that y. So in order to find the derivative of g, we're going to use the derivative of f. So what is f prime of x? We need to know what that is. Well, since we have the formula for f right here, its derivative would be 5x to the 4th minus 3x squared plus 2. And all I have to do now is plug in 1 into that function to figure out what this denominator is going to be. So if I plug in 1 into that, I'm going to get 5 times 1 to the 4th minus 3 times 1 squared plus 2, which is 1 over 5 minus 3 plus 2, and that's 2 plus 2, or 4. So the derivative of g at 2 was equal to 1/4. So to summarize once more, if you want to know the derivative of an inverse, but you don't have that inverse function available to you, what you can do is take the derivative of the original function f, take its reciprocal evaluated at the output of your g of a or g of 2, whatever that input value happens to be. So if we wanted to know g prime of 2, we needed to find out what x value for f made that function equal to 2, and that's the number that we're going to plug into our derivative of f. Okay, so it's a little bit complicated, but essentially the idea is this reciprocal relationship. The derivative of y with respect to x is just 1 over the derivative of x with respect to y. So that inverse relationship or reciprocal relationship between our inverse functions. Now the main idea of this video lecture is in deriving the derivatives of our inverse trigonometric functions. So we're going to start by deriving the derivative of tangent. So if we wanted to know what the derivative of the inverse tangent function is, the first thing I'm going to do is I'm going to create a new function g, which is this inverse tangent. So you can write arctan if you want, or you could use that little tangent with the -1, which means inverse tangent of x. Okay, so according to this formula that we just talked about, g prime of x is 1 over f prime of g of x. So what we need to do is plug into f prime whatever g of x is, and our g of x is this inverse tangent function. But we need to know what f prime is, so if f of x is tangent of x, what is f prime of x? And this is something that you should have memorized. What's the derivative of the tangent function? It's secant squared. So f prime of x would be secant squared of x. So what would f prime of inverse tangent of x be? Well, here our input is inverse tangent of x. So that's what's in this little space here, and that's what needs to go right here. So we want to plug in inverse tangent of x right in there, right in that argument for secant squared. So this becomes secant squared of inverse tangent of x, just like that. Now, in order to figure this out, we're going to use a few identities. We know that secant squared is the same as tangent squared x plus 1. That comes from some of those Pythagorean identities that you learn in trigonometry. So what I'm going to do is change this secant squared of inverse tangent to a tangent squared of inverse tangent plus 1. I just substituted in that identity where this box became this box right here. Now the reason I'm going to do that is because the tangent and the inverse tangent are going to end up canceling each other out. And all we get is that x, but it's being squared, and it's all in the denominator. So what we end up with is that the derivative of this inverse tangent function, this g of x, it turned out to be 1 over x squared plus 1. So that's kind of strange because it just proved that the derivative of an inverse tangent function, an inverse trigonometric function, turned out to be an algebraic function, a polynomial of sorts. Okay, so it doesn't even have any trigonometric functions left in the answer, which is kind of surprising. So this shows that the derivative of an inverse trig function is an algebraic function, just like the derivative of the transcendental function ln of x is also algebraic, and you get 1 over x when you take the derivative of an ln. Now, some of the other derivative rules that we're going to have to know, and you will need to memorize these, are the following. And these are some generalizations using that chain rule. So the derivative of an arc sine, or an inverse sine, if you will, is 1 over the square root of 1 minus u squared times that u prime. So whatever this u is right here, that goes down here, and its derivative goes on top. Arc cosine, or the inverse of cosine, has the same exact rule, but it has a negative out front. Now the derivative of arctangent is the one we just derived. We got 1 over 1 plus x squared. In a more general formula, if this is any general u, you're going to get a 1 over 1 plus u squared and the derivative of that u on top. And if it's a cotangent, you just get a little negative in front. And then finally for inverse secant, you're going to get 1 over the absolute value of that u times the square root of that u squared minus 1, and all of that times u prime on top. And inverse cosecant is the same thing but with a minus. Okay, so these are kind of complicated, but you'll see some patterns if we look at these. You'll see that the sines and the cosines have a square root with a 1 minus u squared in the bottom, whereas the secants and cosecants have a square root with a u squared minus 1. So the order matters there. And for the secants and cosecants, you also have that absolute value of u on the bottom. For tangents and cotangents, there's no square root. It's just the sum of the squares, 1 plus u squared on the bottom. So let's practice using these. Now we're going to prove the derivative rule for arc secant first, and then we're going to apply it. And I'm going to prove this one in a slightly different way. We're going to use a little bit of implicit differentiation to prove what this derivative rule is. So suppose we wanted to know the derivative of arc secant of x. What I'm going to do is I'm going to let y be the arc secant, the arc sine of x. And because of that definition, that implies by our inverse trig functions that x must be the sine of y. If you take the sine of both sides, you'll get sine of y on the left, and the sine of arcsine, those cancel out, giving you just x. So this is just that inverse relationship between sine and arcsine. Now by doing that little change, what I'm going to do now is take the derivative using implicit differentiation of the left side and set it equal to the derivative of the right side with respect to x. This is that implicit differentiation. The derivative on the left side will just be a 1, and the derivative on the right side is going to be the following. Start with your outer function. The derivative of sine we know is cosine. So this is going to be cosine of y, but because this has a y term in it, remember in implicit differentiation, you always multiply your y terms by that y prime, because that would be the derivative of the inner function with respect to x. So we get 1 on the left, and we get cosine y prime on the right. Now to solve for y prime, we would just divide by cosine of y, and that means that y prime is equal to 1 over cosine of y. Now I'm going to do a little bit of manipulating here. Remember our trig identities, our Pythagorean identities. We know that sine squared y plus cosine squared y is equal to 1. Therefore, cosine squared y is equal to 1 minus sine squared y. So if I take the square root of both sides, cosine of y will be the square root of 1 minus sine squared y. And what was sine of y? Remember, sine of y was just x. So cosine of y becomes square root of 1 minus x squared. So this becomes 1 over the square root of 1 minus x squared. And that's exactly the rule that we have up here for arc sine. 1 over the square root of 1 minus u squared times u prime. That would be the generalized form of it using the chain rule if this u is a function of x. But if this was just an x, then derivative of x or x prime would just be a 1 on top. Okay? So let's practice. These are tricky, but it's really just a formula that you're following. So we want to differentiate the derivative, find the derivative of arc secant of 2x. So first of all, let's review our rule for arc secant. It's going to be u prime over the absolute value of u times the square root of u squared minus 1. So let's write that down over here. So the derivative is going to be u prime over the absolute value of u square root of u squared minus 1. And our u is this 2x. So the derivative y prime is going to be the u prime. Derivative of 2x would just be the 2. And then on the bottom, we're going to have the absolute value of our u, which is just that 2x, times the square root of our u quantity squared minus 1. And if you simplify this, this 2 can cancel that 2, so we'll have 1 over absolute value of x square root of 4x squared minus 1. And there's our derivative. Okay, if we go to the next one, y equals 2 ln of t squared plus 4 minus arctan of t over 2. So to start off, y prime is going to be the derivative of this 2 ln of t squared plus 4. Remember that the derivative with respect to x of ln of stuff is stuff prime over stuff. So that's what I'm going to use here. The 2 out front stays put. This is my stuff, so it goes in the bottom. And the derivative of that stuff would be a 2t. So there's the derivative of our ln part. Now we want to subtract from that the derivative of our arctan. So our rule for arctan says that the derivative of an arctan is the u prime over 1 plus u squared. That comes from right here. Okay? So in this problem, our u is this t over 2. So what would be u prime? If this is u, what's the derivative of that? T over 2 is like a 1/2 t. So the derivative of a 1/2 t is just a 1/2. So u prime is just a 1/2. And then on the bottom, we want 1 plus this u squared. Now that's going to simplify a little bit. Let's go ahead and multiply my two 2's together. So this becomes 4t over t squared plus 4 minus 1/2 over 1 plus t squared over 4. And I have a lot of fractions here, so I'm going to multiply by a common denominator of 4 on the top and on the bottom, just to simplify that fraction a little bit. So this first one will stay the same. 1/2 times 4 is just 2. And make sure you distribute that 4 to both of the terms in the bottom. We'll get a 4 plus a t squared. And now these two denominators actually match. So we have a common denominator here of t squared plus 4. So we can go ahead and subtract the two numerators and make it 4t minus 2 all over t squared plus 4. So there's our derivative. Okay, the next one, we want the derivative of arc sine of e to the 3x. So our derivative rule for arc sine of u is u prime over the square root of 1 minus u squared. And this is our u. So the derivative y prime is going to be u prime on top. What's the derivative of e to the 3x? That requires a chain rule. You're going to get e to the 3x right back again times the stuff prime, and the derivative of 3x is a 3. So all of that is our u prime. On the bottom, we want the square root of 1 minus that u squared. So if we simplify, this becomes 3e to the 3x on the top, and on the bottom you have a power to a power, so you get to multiply. 3x times 2 becomes a 6x. So this is 1 minus e to the 6x. Okay, and then our last example here, we want to find the equation of the tangent line to the graph of the equation arctan of xy equals arc sine of x plus y at 0, 0. So if you want the equation of a tangent line, you need to have a slope of a tangent line, and a slope of a tangent line is a derivative. And unfortunately, this equation has our x's and our y's mixed together. So this is an implicit equation, which means we need to use implicit differentiation. So that requires taking the derivative with respect to x of the left side and setting it equal to the derivative with respect to x of the right side. So we're going to need some derivative rules here for arctan and arcsine. So for arctan of u, the derivative rule is u prime over 1 plus u squared, and the derivative rule for arcsine of u is u prime over the square root of 1 minus u squared. So this is my u and this is my u. So according to this rule, we're going to need u prime on top over 1 plus u squared. Well, let's do the bottom first. The 1 plus u squared would become 1 plus xy quantity squared. There's my 1 plus u squared. That's the derivative of this arctangent part. But on top, I would need u prime, and that's the tricky part because u is x times y. This is easy to overlook, but you do have a product in between these two terms. This is an x times a y, so you have to use a product rule to get the derivative of that u. So the product rule is going to be the first times the derivative of the second plus the second times the derivative of the first. So the first would be x, and the derivative of the second is y. Now remember, in implicit differentiation, when you take the derivative of a y term, you need a y prime. So the derivative of y wants to be a 1, but then we have to multiply that by a y prime. So there's first times derivative of the second plus the second, which is our y, times derivative of the first. And the derivative of x is just a 1. So all of that on top is our u prime over our 1 plus u squared. On the other side, we want the derivative of an arc sine. And that's going to be u prime over the square root of 1 minus u squared. So on the bottom, we're going to want a square root of 1 minus this u squared. And what would u prime be? Well, the derivative of u is going to be the derivative of x, which is 1, plus the derivative of y, which should be y prime. So let's clean it up a little bit here. We're going to get an x y prime plus y over 1 plus xy quantity squared equals 1 plus y prime over the square root of 1 minus x plus y quantity squared. Now, as you can imagine, trying to solve this for y prime is going to be a big mess because we have lots of fractions and radicals and all kinds of things going on. And remember what we're trying to do for this problem. We're trying to find the equation of the tangent line at 0, 0. So once we found our derivative, what would we normally do? We would plug in 0 for x and 0 for y and find out what that slope is. So I'm going to show you a little trick here. Instead of going through all the work of solving this for y prime, which we could do, but it would take a long time, instead, since we know we only want this derivative at 0, 0, let's go ahead and plug in x equal to 0 and y equal to 0 right at this stage, and then solve that for y prime. So I'm going to substitute in a 0 here, 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 and here. So 0 times y prime is going to go to 0, plus another 0. So this whole numerator is 0. On the bottom, we get 1 plus 0 squared. And over here on the right, we get 1 plus y prime over the square root of 1 minus 0. So simplifying that, the left side is obviously going to be 0 over 1, which is just 0. And the right side is going to be 1 plus y prime over 1, which is just 1 plus y prime. And that means if I solve this for y prime will be negative 1. And that y prime is our slope m. That's our derivative. So this is the slope of our tangent line. So therefore the equation of our tangent line is going to have a slope of negative 1, and it's going to go through this point 0, 0. So that would be y minus 0 equals negative 1 times x minus 0, which is just y equals negative x. So without doing all the menial labor of solving for y prime, we just plugged in our zeros right away, and that gave us an easy way to solve for y prime with a lot less hassle. And that gave us our m, and then we could use point-slope form to get our equation. Alright, so I'm just going to back up here one last time. You do want to have these 6 formulas memorized, the derivatives of your inverse trigonometric functions. You will see them occasionally, so try to have these memorized. Alright, that concludes our lecture on derivatives of inverse functions. Good luck.